Hello, good day, ladies and gentlemen. Welcome to our today's webinar focused on designing of concrete structures. The name or the title is Frame Corners, which is a common problem of discontinuity regions, and we will show you today how to tackle this problem easily. Today, I'll be just moderating this webinar, because the main speaker is my dear colleague Orsi, who will guide you through this webinar. Orsi, can you test your sound and tell us how are you feeling today?
Hello everyone, thanks Adam for the introduction. I'm feeling great. Spring is finally coming to Brno and I am so ready for this season.
Very good. And we also have a nice lunch ahead of us after this webinar, so we're excited. All right, let's move forward. For the introduction, we are running this webinar on the platform GoToWebinar. You can see the panel on your screen, and there feel free anytime to click in the questions panel and type in your questions. We will be answering those questions during the webinar via this questions panel, so by text. We will then at the end of the webinar pick some of those questions and answer them loudly. And if we don't manage to answer all your questions, we will send them later by email, the answers to them. All right, that's for the organization. So questions panel, once again, feel free to ask anything. And for the agenda, so we will look today at the topic of frame corners in concrete structures. So these type of detail arises among different kinds of buildings or technical constructions, whatever. And it's at the one hand very simple thing to deal, very common thing, but on the other hand, it's not that easy, and there are certain uncertainties which Orsi will explain you and guide you through how to tackle them, what are the typical solutions here, what can go wrong, and how to avoid this. And she will show you this all on a practical example in the IDEA StatiCa Detail application. All right, so let's move on. That's it from my side for now, and I will pass the presenter to Orsi, and she can start.
Thanks Adam. Can you please confirm if you can see my screen? Thanks. So let's get into the topic of frame corners. So let's start out with a little bit of theory. Frame joints or frame corners in reinforced concrete structures are among the most failure-prone details of cast-in-place reinforced concrete structures. And while this is true, they are often overlooked or not treated as typical D regions. Frame corners can represent a joint between a beam and a column or a plate and a wall. They can be present in precast stairs or other precast structures where a frame corner is apparent. Frame joints are also in integral bridges or in tunnels. This will be the practical example today. So on the right side, you can see some typical frame corners that engineers are dealing with during their designs. So why are they special? Why we planned even a webinar for this topic? So in frame joints, the beam theory, the Bernoulli hypothesis, does not apply about planes remaining plane after deformation. And this fact makes them a typical discontinuity region, or D region, in other words. Discontinuity regions require special attention during analysis and design, and there are some approaches to deal with them. How are discontinuity regions typically designed? So one widely used approach is the strut-and-tie method. And another one is a nonlinear finite element analysis. Let's talk about these most widely spread methods. So the strut-and-tie method replaces the complex stress fields that are appearing in concrete structures with concrete struts, which are in compression, and reinforcement ties. Those are the ones that are in tension. In the places where these struts and ties intersect, there are nodes. And the main advantage of this method is its simplicity that can be calculated by hand. And the method is also recognized by most codes. The main disadvantages are the fact that it is quite a time-consuming calculation, and it requires a lot of engineering judgment, mostly because multiple valid models can exist for the same structure, and the engineer has to pick the right one for his or her design. On the right side, you can see some typical strut models, strut-and-tie models for frame joints loaded in negative or positive bending moments. About nonlinear finite element analysis, these are advanced numerical modeling. Now I'm talking about modeling in software such as Abacus, ANSYS. In these softwares, you can model concrete cracking, plasticity of materials, concrete reinforcement interaction, and you can input constitutive material models. The main advantage is that it allows you to detailedly capture the stress and crack distribution, and it can simulate failure mechanisms. However, the main disadvantage is it requires a lot of expertise, and it is really sensitive to modeling assumptions, so it is not really practical for routine design in engineers' everyday work. We came with a third approach. The method is called compatible stress field method, or CSFM. This is an advanced nonlinear finite element calculation, which was packed into a practical design tool for everyday engineering tasks. The method CSFM is an evolution of the strut-and-tie method and stress field methods, while it removes their main disadvantages. Let's talk about the method and its basic principles. So we are calculating in plane stress. It is a 2D vertical model. The concrete does not act in tension, and all tension must be transferred by reinforcement. The compatible stress field method considers compression softening of concrete. This is realized using a KC factor. We will talk a lot about this KC factor later during the practical example. The main thing is that we are reducing the compressive strength of concrete in the places where big tensile, transverse tensile strains are present in the structure. The method considers tension stiffening of reinforcement, and the material models defined in the method are by design standards. This method allows you to see the realistic behavior of the cracked structure, and it provides code checks for both ultimate limit state and serviceability limit state, so you receive results for crack width and deformations too. What are the possible failures that can affect a frame joint? So the failure modes can be divided by whether a frame joint is loaded by positive bending moment or negative bending moment. The frame joints loaded by positive bending moment, the failures that can happen here are, for example, tensile reinforcement reaching its load-bearing capacity, or concrete failure in compression due to transverse tensile stresses. Or there can be compressive failure of concrete due to spalling of reinforcement cover, or a failure of the anchorage zone of the tensile reinforcement. You can see a typical strut-and-tie model of a frame joint loaded by positive bending moment and the required reinforcement that was designed based on this model. And what happens when you have a big negative bending moment in a frame joint? Tensile reinforcement can reach its load-bearing capacity. Concrete can fail in compression. There can be failure of the reinforcement anchorage zone due to transverse cracking, or there can be spalling of a concrete cover layer. In frame joints loaded by negative bending moment, there are several approaches that the engineer can choose when designing, for example, based on the strut-and-tie method. One simple approach can be that in this transverse direction in the frame joint, you can pick one concrete compressive strut, a straight one, but in that case, you have to be aware that where a concrete compressive strut is forming, there can be transverse tensile strains appearing in concrete, and you somehow have to catch these tensile strains, typically using reinforcement. There are approaches in the literature how to do that. You can either add detailing reinforcement, which is typically designed to 0.25 times the force in the compressive strut. So you catch the tensile forces that are equal to 0.25 times the compressive force by reinforcement. Or you can introduce a more sophisticated strut-and-tie model when you actually create this bottle-shaped strut, which is made of these struts that you can see here, and in between them there are ties forming, and this way you can get the exact forces that are in these ties and design the reinforcement based on that. Or if you have the tool that allows you to design the reinforcement in a different way, such as the compatible stress field method, you do not have to build such complicated strut-and-tie models at all. But we will talk about this in the practical part. So here we have our first poll question, and I will give the word to Adam to launch this poll for us.
Yes, so this is my other 2 minutes of fame now. So I will take over this polling. So you can see the question. We are interesting to know how you do it now, how you deal with these frame joints, whether you use strut-and-tie or other approaches. So I will launch the poll. You should see the blue screen now. If you maximize the go-to screen, you should be able to poll, choose one answer from the list, and we'll be interested what comes out of this. Isn't it, Orsi? How do you feel about this when you based on your previous experience being designer? Would you go for strut-and-tie or rather some advanced softwares?
So during my work in design office, we did a lot of designs mainly for integral reinforced concrete bridges. So we designed a lot of frame corners, and honestly, sometimes we used strut-and-tie method when the loads were pretty high and the solution was not so obvious. But we also relied heavily on engineering judgment, mainly by the most experienced older colleagues. And I guess we over-designed the frame joints by a lot. So I would say that if we would have a tool to optimize the solution, probably we could save some reinforcement, because those frame corners were pretty heavily reinforced, to say the least.
Let me see. Okay, very good. So let's close this poll and take a look at the results. So most of you voted basically the same opinion as Orsi just mentioned, either strut-and-tie or the engineering judgment, or let's say the experience of how is it usually done. So yeah, good. Thank you for this poll. And I will hide this polling, and Orsi, you can continue.
Okay, so now is the time to start our practical example. It will be a frame corner of a backfilled tunnel, which is a real example of a tunnel in the Czech Republic. As you can see, it is a simple reinforced concrete frame structure, which is supported on piles. You can see some photos from the construction site here. The global model of this frame was created in CSFM Engineer, and the frame joints were analyzed, reinforced, and co-checked in IDEA StatiCa Detail. So how did the design process look like? The engineer created the global model in CSFM Engineer with the appropriate support conditions. As I said, it was supported on piles. He added loading, created combinations, and explored internal forces. In the right picture, you can see how the loads look like. So from the sides of the tunnel, there was some earth pressure from both sides, and also from the upper side of the frame, there was the weight of the overburden above the tunnel. After the combinations were created and analysis was completed, the normal forces, shear forces, and bending moments were read from the global model. The engineer extracted the internal forces that were relevant to the analyzed frame joint part of the structure. We will be modeling a 1 meter thick cutout segment of the frame joint, not the entire frame. So we will need to load the cut end with internal forces from the global analysis. Now I'm talking about this right edge that is basically cut out of the structure. The bottom edge will be supported in our model in IDEA StatiCa Detail by a rigid support. The displayed internal forces that you can see here are considered in characteristic values for the 1 meter thick segment. So we will input such a frame joint detail into this application detail, and we will load it, as you can see here. From the left side, we will input earth pressure into one load case. From the upper edge, we will input the weight of the overburden about the tunnel, and to this right edge, we will need to input this set of internal forces from the global analysis. How do we do that? How do we input internal forces as outer load? I will show you in the application. So let's start actual modeling. So I will launch IDEA StatiCa and start the detail application. In this example, I will show you how to import the whole model basically from scratch from a DXF file. So we will stay in the 2-dimensional module of detail, and we go into the general input where we do not have any template. The concrete will be set C3545, reinforcement B500B, and the concrete cover will be set as 50 millimeters. So I click on Create Project, and basically an empty project will be loaded where I can import from a DXF file my geometry. I have a DXF prepared with the outline of the frame joint and also the reinforcement. So let's at first import the outline of this member, clicking OK. What I have to change here is I have to set the thickness of this frame corner. It will be 1 meter. The material was set automatically based on the settings before. I have to support this structure, so the support will be input here. Supports can be found in model entities. I will pick a line support, set the edge as number 6, and remove the compression only functionality, so this support can transfer both compression and tension. So what we have to input now are the load cases. So I'll go back to the presentation for a little bit and show you what we will input. So we will have 3 separate load cases, one for the air pressure, one for the overburden, and one for the internal forces input. How to input these internal forces onto a section? One approach could be to use our application RCS, which stands for Reinforced Concrete Section, to receive the response of the section. So I create a 1 meter wide section. This is exactly the section that I will input loads on in detail, which is 900 millimeter high, 1 meter thick. I have some reinforcement input to the upper edge. These are 10 reinforcement bars with the diameter of 25 millimeters. I input internal forces on the section in characteristic values. These are the internal forces that came from the global analysis of the structure. And from this input, I receive the response of the structure. So I know that this combination of internal forces causes a tensile force in the upper reinforcement and some compressive force in concrete. Here I see stress values, but from these stresses, I can calculate actual forces. So the resultant force in the upper reinforcement layer, this Ft, will be the stress in reinforcement multiplied by the area of reinforcement. So I receive this value 67.1 kilonewton. This is the point force that I will input into the reinforcement in the detail application. And similarly, I will input triangular loading onto concrete to input the forces into concrete that came from the combination of normal force and bending moment. How do I input a point force into reinforcement so it is transferred directly into the reinforcement in detail? There is a way using a patch device or a patch load. This is a load transfer device in the application detail that can be used to transfer some force directly into the reinforcement. It is input into a defined position in the detail model, and it is connected with a reinforcement. Then whatever point force is input into the patch device is transferred directly into the reinforcement. The resultant force from normal force and bending moment into concrete can be input as a triangular load. I will show you how it is done. And we also have some shear force at this end section. We also have to input it as a vertical line load. You can notice that the shear force will not be input in the exact edge of the concrete. The reason for that is that if I input this really concentrated vertical line load into the edge, during the numerical calculation, this edge will tend to fall off, so to say. So the calculation will not be running until the end because there will be some criteria reached, because we would load this technically unreinforced concrete edge by a big vertical line load. So I will put it a little bit into the concrete volume so it is transferred better into the structure. So let's do it in the application. I will input 3 load cases, LC1, LC2, and LC3. I will rename them so we know which one is which. This will be earth pressure, second one will be overburden, and the third one will be the set of internal forces, normal force, shear force, and bending moment. So the first ones are the easy ones. Let's input some line load for the earth pressure onto the edge number 5. It will act in the global X direction horizontally on the whole length of the edge, and the values will be 52.5 and 74.8 at the end, like this. So this is the load from the earth pressure. The overburden, here I will also input line load, but on the top edge number 4. It will work in the global Z direction vertically and with the value minus 105 kilonewton per meter. So we have these first 2 load cases set. The third one, which is the most complicated one, here we need to input shear force, normal force, bending moment. We have to input a point force in the upper reinforcement and some triangular load into concrete and also some vertical line load. As I was talking about this point force input during the presentation, I will use the model entity of a patch load, which is a load transfer device, and place it in this area where the top reinforcement will be. So to make it a little bit easier, I will import from the DXF file the reinforcement, so I know where to place the patch device. So let's import the prepared reinforcement that we can edit later. Select. So we have some reinforcement at least, and I will place this patch device here so the point force can be transferred into the reinforcement. So the master point will be point number 3, and the position related to that will be 7 centimeters lower. So here, what is also important to do is to connect this patch device with the reinforcement that I want to transfer the forces into. So to do that, click on the reinforcement, and here is the option to interconnect automatically patch loads or patch supports with the reinforcement. By doing that, I have connected the patch load with the reinforcement, and now whatever point force I input into this patch device will be transferred into this upper reinforcement. So let's input this point load. It will be a horizontal load with the value 67.1 kilonewtons, and the transmitting device was set automatically as this load transfer device, this patch device. Now we need to input triangular load into concrete, which will represent the combination of normal force and bending moment. To do that, I will set it. It will be a horizontal load on edge number 3, and it will not be on the whole edge, but just a part of it. Let's change the values to 0. So it is a triangular shape. It is set from the beginning, and the length will be 0.53 meters. So just like that. And what is missing here is the vertical load representing the shear force. So I will add another line load that will be vertical in the Z direction. The intensity will be minus 640 kilonewtons per meter, and I will define it by 2 points. The master point will be point number 3, this upper corner, and the position has to be set as minus 5 centimeters. Like that. Okay, so we don't have this vertical shear load acting on the edge of the frame joint, but a little bit into the structure, so it can be better transferred during the numerical calculation. So this way we input this set of internal forces into this frame edge. And what needs to be done now is we have to create combinations out of these 3 load cases, because we are calculating a nonlinear calculation here. We are not calculating load cases, but combinations. So we need to create 2 combinations in this case. One will be for ultimate limit state, and the second combination will be for serviceability characteristic combination, which will be used for the crack width check and the deflection check too. By clicking on this pen, I can change the factors for the loads. So for ultimate limit state, I input 1.35 for all of these permanent loads. And now we have the combinations set. I have imported this set of reinforcement bars from DXF, which serves basically as a template for me now, because as we can see in the 3D view, it is the just one layer of reinforcement imported into the middle of this frame joint. Now I have to set how many of these bars I want in one layer, and I can define all the things regarding reinforcement now. So this main corner reinforcement will be made of 25 millimeter rebars. We can set the anchorage type at the beginning, at the end. I will have continuous rebars continuing into the column here, and I will have 10 bars in one layer. Also, we have to change the mandrel diameter, so we do not have such sharp corner. Now let's set this rebar here, which will be 60 millimeter anchorage type. I set it like this. 10 bars in one layer. This vertical bar will be made of 20 millimeter diameter bars with the anchorage type set like this, and the number of bars in one layer will be 5. Let's set this horizontal bar. 60 millimeter is okay, and let's set the anchorage, and the number of bars will be 10. Now I will define the stirrups. So I want to set them as a group. They will have 60 millimeter diameter and perfect anchorage at both ends, and number of bars in one layer will be 4. What we are missing here, this detailing reinforcement, I will input it as like this and define the anchorage shape like that. 5 bars in one layer, and again find 5 bars in one layer. So let's take a look at the real 3D view. Now it looks much better. And for the first calculation and for the demonstration purposes, I will turn off some rebars and leave just this basic reinforcement setting, what you can see here. So we run a first calculation with these ones, and I will show you a couple of results on this reinforcement setting. So what you see here is the calculation stopped, and what the information says here, the divergence of nonlinear calculation happened. You can read that only 99% of the applied loading was successfully applied during the calculation. What I do now, I go into the check results and explore what is wrong, what happened here. Why is the model not transferring all the loading? I go into the auxiliary results, and what you see here is this corner is deforming quite weirdly. This corner is somehow splitting away, or there are big deformations. If I go into the tensor concrete values and turn on the epsilon1, the principal strains in concrete, I can see that in this corner I have big tensile strains, and this was probably the reason of the calculation stopping. Why is this? Going back to the design, it goes to this load case again, when I was applying really big forces on this technically unreinforced concrete cover. So to avoid this problem during the numerical calculation, I input this rebar that you can see here, which will act as a bracing of this concrete edge. I will input quite thick rebars here. Let's input like 5 rebars into one layer and anchor them perfectly. And this rebar will serve as a strengthening, bracing purpose to transfer this concentrated load into the structure so we can calculate successfully. So let's see what this does. Now you can immediately see that the results look much better. We don't have any non-conformity messages here. The ultimate limit state results already look all green. What needs to be checked now? I go to the check results. Let's say go from the beginning. So at first you would see the summary of results, where you can see that we have a quite massive concrete strut forming in this structure, as it is expected. In the auxiliary results, if I check it in more detail, I can display the principal strains again. Look at this corner. Now it is behaving normally. There are no big extreme strains happening there. But what I see here, I have a area where there are big tensile strains. I can display also their directions. And these are these transverse tensile strains that I talked about that are happening in these concrete compression struts when we have this bottle-shaped compressive strut, and in the transverse directions there are big tensile strains appearing. So what is with this tensile strain? If I go to the strength results, what I can check out is the KC2 factor. This is a compressive strength reduction factor. This is a factor that reduces the concrete compressive strength in the areas where we calculated that we have big tensile strains happening. So this KC2 factor is used for ultimate limit state, and it reduces the strength of concrete. So the ultimate limit state results are on the safe side. What we do not know now, if I go to the crack width results, you can see that we are displaying cracks in the proximity of reinforcement. This is because the implemented method, the compatible stress field method, is able to calculate cracking of concrete, their appearance and their width in the proximity in the surroundings of reinforcement. But if I have big areas in concrete that are unreinforced, I technically do not get any information of the cracking there. So the only information I know is from the auxiliary results that here I have big tensile strains, but since I don't have any reinforcement in this area now, I don't see the cracking there. So what is the recommendation? If you see that somewhere you have big tensile strains, probably there is some cracking forming, put at least some reinforcement bars, at least for detailing purposes. Even some thin reinforcement can be sufficient there to check out whether the concrete is cracking there, and so you can catch those tensile strains there. So now I have completed my reinforcement setting with these horizontal rebars, and let's calculate the model again and let's see what changes. Going to the check results. And do the crack width results. Now you can see that we have now information about the crack width even in this area, and you can see that we have quite big cracks forming around this reinforcement. The limit crack width was set as 0.3 millimeters, and here we have about 0.4 millimeters. So what can be done to prevent such cracking here? One thing could be to increase the reinforcement size, either the diameter or the number of bars. But another trick I want to show you in frame corners, which can be found also in many books talking about frame corner design, is to change the diameter of the mandrel here in this corner reinforcement. You see that the default mandrel diameter the one that I input was 7 times the diameter of the rebar. Let's change that to 25 times the rebar diameter to make this corner make this diameter bigger, and calculate it again, how it affects the behavior of the structure. Now you can see that the crack width was reduced here to about 0.18 millimeters, and now the crack width results are satisfying from the code perspective. So I didn't need to input additional reinforcement. I just changed the mandrel diameter, and the crack results were immediately improved. Because with this, I changed the forming of the concrete compressive strut. If I look at the strength results and display the stresses in concrete, you see that now I don't have such markant thin concrete compressive strut, but it is much wider, and it distributes the stresses better, so it has a positive effect on the cracking. So ultimately, my state is all green cracks are dealt with. What is missing here is the stress limitation. We are not fulfilling the stress limitation check. So just check it out. You can see that in this corner, in this small surrounding of this corner, we have exceeded the limit stress in concrete. This is something that can happen in numerical calculations. Often we call these singularities, that in the small surroundings of corners, we can exceed the limit stresses. And for this issue, we have a functionality called limited check here. So what is this? I click on F1 to open the article from our support center. And here you can find an article that describes what this limited stress check feature does, how it can be safely used, how an engineer can differ or decide whether the stress concentration is a true singularity or it is a stress concentration that cannot be neglected. And basically what this functionality does in detail, if I turn it on, is excludes these small areas where the stress is above the limit, and it gives you also the information that this functionality was used based on what chapter in the code. So basically, we have completed the frame joint design, and we have an optimized reinforcement solution in this example. Let's go back to the presentation whether I have something left there. So we have input loads. So to conclude the webinar and to give you the main takeaways of what was the purpose here, what I want to recommend you is do not rely solely on the all green results. Check the tensile strength in concrete, check the KC factor where the compressive strength of concrete is reduced, get familiar with the auxiliary results, check the principal strains, their direction, and add additional reinforcement, at least for detailing purposes and for the crack result check, so you get the whole picture and you can have a realistic view of the behavior of your structural detail. The result, if you do all this, you can be fully confident in your design and in the fact that the app design is as optimized as it can be. Now we got to the second poll. I will ask Adam to launch it for us.
I'll certainly do. I'm still here. So, a second poll of today's webinar, another question from us towards you is, after seeing this and understanding how detail works and what it can do, what you designers, engineers dealing with concrete structures of all kinds, what are the other problems or options you would see detail to be useful? So let's launch the poll. You can start voting. So in this poll, I put on the first place the frame corners, which is the topic of this webinar. So obviously that would be one of the answers. But also imagine prefabricated or cast in situ walls with openings. So these typical panels for modular concrete structures, or even the complex ones where you can have multi-stories and very big walls with a lot of openings for windows and doors, whatever. Or it can be all sorts of beams of irregular shapes. Imagine openings, these lightened beams, depth ends, all sorts of those. Also pre-stressing included in those beams. Again, prefabricated or cast in situ, post or pre-tensioned. So all kinds of those. Column pedestals, that's quite obvious, including the anchoring of the columns if they are made of steel, perhaps, if you deal with those as well, and the pile caps, bounding multiple piles into one block. All right, so let's close this poll and share the results. So quick thoughts. Frame corners is the winner, obviously, topic of this webinar, but walls, beams, and pile caps, also high numbers. And Orshi, do we have solution for those in the detail right now?
Yeah, we do.
Okay, so what we can do is recommend to our attendees today to look at our webpage, ideastatica.com, and browse especially the support center and the tutorials for these topics all covered. All right, so let's hide this and continue the questions and answers, right?
Yeah.
So I can see in the question panel, we are managing to answer your questions during the webinar. And let's pick some of these questions and read them aloud. So I have first one from Chris, and he asks, what is the KC factor for concrete, and where can I get the information about it, how to get it? Rephrasing the question, Orshi, would you know?
Yeah, thanks for the question, Adam and Chris. So yes, we talked a lot about this KC factor in detail. So let's show you how you can find more information, read some articles or some theory behind this. If you go to our main website and into the chapter support and learning, here we have a support center where you can find all sorts of materials, tutorials, webinars, videos, verifications. But now I will show you the theoretical background, which explains the main principles behind our applications. If I choose the concrete and the detail 2D, which was demonstrated today, and I go into the theoretical background document of this application, I can choose these main assumptions and limitations, where are the main things described about the method. And here you can see how the KC factor is taken into account. So it is calculated as a reduction factor for the concrete compressive strength. Here is the formula, how it is applied, and some more information about it. So for the people who are interested in this theory, everything can be found in the theoretical background document about the method, about the application, all of that. Do we have another question, Adam?
Yes, I pick another one. Very good question from, who was that? David. And let me read this aloud. So in your experience, what is the most common modeling mistake engineers make when designing frame corners? Okay, so Orshi, do you have experience from perhaps our help desk, or when you speak to our users, or back then from your practice times as designer?
Yeah, so the thing is that sometimes engineers leave quite big areas of concrete unreinforced, and they are not checking the tensile strains in those unreinforced areas. As I was showing in this example, when I removed those rebars and I had this a big area of the frame corner unreinforced, I didn't know if the structure was cracking there or not. So this is a common thing that we see, that they do not add any reinforcement into some areas, and then they do not get the crack results there. So to avoid that, at least detailing reinforcement even into the areas that do not appear to crack on the first glance.
All right, thank you. Good. Thank you very much, Orshi, for answering those questions. I would move on because we're running out of time dedicated to this webinar. So let's get to the final conclusion. I will take the presenter and show you the last part of the presentation. So we're leaving questions and answers. Thank you for your questions again. There was one last question that I would like to answer aloud. If the recording and materials will be available after the webinar, the answer is yes. Today later we will upload the recording to YouTube and our webpage, and all of you will also get automatic email with the link. So don't worry, you can review this webinar and share it perhaps with anybody interested as you wish. All right, so let's conclude this. Orshi, this was excellent. I am astonished. It was a great webinar. Thank you. And for the next webinars ahead of us, for those of you interested in steel structures, in late March, we are running a webinar which is called Connection Wednesday series. This time we will be focusing on a modeling of complex haunches, a moment connection with all the aspects around it, how to set the model properly and get the best results for the least work. And in April, the new version of IDEA StatiCa is coming out, the version 26.0, with a couple of improvements. I can mention a little sneak peek. We'll be improving our member application for stability and buckling assessment. So stay tuned, and we will explain this in the webinar at the end of April. So keep an eye on our webinar offers, and we'll be happy to see you again. After the webinar, you will get a short survey. Please fill that in if you feel so. The recording I mentioned, Support Center and YouTube, available today. If you are not our users, would you like to try the software, just click on the web page to get a free trial. It has full functionality for 2 weeks, so you can try it thoroughly out. And in the support and learning part of our web page, that's the support center where all the tutorials and the articles Orshi was showing you during her presentation are available, and you can browse them, read them, and use them. All right, one last thing is we also, next to tutorials and articles have these campus courses. So this is also free. If you navigate again to this support and learning part, you can click on e-learning campus, navigate to these 3 concrete courses that we offer, and especially this one, structural design of reinforced concrete, that you can take. You will learn a bit of the theory, a bit of how to use our apps regarding this topic of engineering. And at the end, you can take a quiz and get the certificate that you are, let's say, educated or expert in this field using our apps. All right, so that is it. Thank you very much for coming today. Thank you very much, Orshi, for this excellent work, and wish you a pleasant afternoon.
Thank you, everyone. Bye.
Goodbye.